I split off the vapor pressure and boiling point into its own separate category in the full thing with the intermolecular forces because it requires a little bit longer of a discussion than some of those other physical properties that result from intermolecular forces do. So we're going to look at vapor pressure, we're going to look at boiling point, and then we're going to look at this thing called the Clausis-Clapeyron equation. So basically, when we change, the external pressure, that's going to change the boiling point of something. And so the Clausis-Clapeyron equation allows us to predict what a boiling point will be at a new pressure, or to figure out what pressure to expect the vapor pressure of something to be at a different temperature. So let's take a look. All right, so let's think about vaporization. We know that, if we spill water somewhere and we don't wipe it up, eventually all of that water will evaporate. Same thing, like if I have a beaker on a bench top and it's got water in it and I just let it sit, eventually it's going to evaporate. We know that the regular boiling point of water is 100 degrees Celsius. And at 100 degrees Celsius, we'll get to that nice rolling boil and our water will evaporate fairly readily. But if I just leave a beaker on the bench top, it's at room temperature. It's not at 100 degrees Celsius. So we still have some molecules that are escaping the liquid phase into the vapor phase, even at room temperature. As long as we're above the melting freezing point of a substance, some will escape into the vapor phase. Now, when I look at the beaker, again, we've got some molecules in an open beaker have enough kinetic energy to vaporize from the surface of the liquid. So we're not, again, at the boiling point, because the boiling point means that we've got enough kinetic energy that we're forming these gaseous pockets in the interior of the liquid. What's happening here is on the surface, a small percentage of the molecules will get the energy to hit the vapor phase. Because remember, what's holding this together are those intermolecular forces, all right? And to go from liquid to gas, we have to break that tether. We have to have enough energy to overcome the energy of the intermolecular force. And so if I'm at a lower temperature, the blue line here, I'm going to have a smaller percentage of molecules with that kinetic energy necessary to reach the vapor phase. As the temperature increases, a higher percentage of molecules will reach that temperature or will reach that kinetic energy necessary to hit the vapor phase. That amount of kinetic energy doesn't change no matter what temperature I'm at. But if I'm at a higher temperature, everything's moving around faster and more molecules will hit that kinetic energy, okay? And so we can look at it, from this viewpoint here, that, T1 versus T2. T1 is a lower temperature, T2 is a higher temperature. And you can see from the particulate view pictures here that at T2, at that minimum kinetic energy to reach the vapor phase, we've got more particles there. And so we have got more particles moving faster at higher temperatures, so more are going to reach that kinetic energy necessary to overcome those intermolecular forces and break those tethers. Okay. Now, what's happening is if we're in a closed situation, we're not just breaking free and escaping. In a closed situation, we're going to have stuff bouncing around in the vapor phase, but then it's not going to have anywhere to go. And so some molecules will escape, but as they're bouncing around, some will recondense, and then some will escape and some will recondense. And so we reach what we call a dynamic equilibrium, okay? At the dynamic equilibrium, the rate of one process is equal to the rate of the other process. It doesn't mean that the number of particles or molecules are equal. It simply means that the rate of the two processes is equal. So the rate at which things are escaping equals the rate at which things are recondensing. So we can look at it this way. All right, so I've got, my vacuum here. We're in there. Now we know that as we fill something with gas, we start exerting a pressure. Okay, so a couple things are happening. We've got, stuff going into the vapor phase, stuff condensing back down. Before we reach that equilibrium, right, we'll be, changing, so that's what the curve is. But at equilibrium, that rate is at that straight line. And so when we're at equilibrium, the same number of molecules leave as enter the liquid within a given time. Meaning that if one molecule escapes the vapor phase, one molecule condenses into the liquid phase. If 5 molecules escape into the vapor phase, 5 molecules will recondense back into the liquid phase. And so the pressure, once we're at equilibrium, the pressure in a closed system is going to reach a constant value. The vapor pressure of this closed system will reach that constant value. Okay? Now, what do we mean by vapor pressure? All right, so vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid phase. All right, so in a closed system, all right, it's all stuck there. Now, most of the time though, we're not in a closed system. Most of the time, we're assessing vapor pressure at room temperature. And so we get a relationship between the vapor pressure and the boiling point. All right, so here I have a graph that shows normal boiling points along with vapor pressure. Okay, the normal boiling point happens to be at 760 torr. Well, what's 760 torr? 760 torr is also 1 atmosphere, and it is the atmospheric pressure at sea level. Okay, and so if we look here, if I am at different, if I have different vapor pressures, I have different temperatures. And so what's happening when we are boiling something is we're looking at this temperature where our vapor pressure is equal to the external pressure. And so I have to get to a vapor pressure of 760 torr, or 1 atmosphere, for the boiling point if I'm at 1 atmosphere. Now let's say I'm not at 1 atmosphere. Let's say, I don't know, my aunt, when I was a child, she moved to a small mountain town near Yosemite that was at high altitude. And she discovered that things work differently at high altitude. She had to alter cooking times and directions. Or let's say I go into my own kitchen and I use my pressure cooker. That changes things too. Because at a different external pressure, we have to get to a different temperature in order to reach that boiling point. Okay? All right, so again, our boiling point is the temperature at which the vapor pressure equals the external pressure okay, and this is usually the atmosphere. Because typically we're doing things in an open container. And so that boiling point depends on that applied pressure. If the atmospheric pressure is lower, then our boiling point is going to be different as well, because that external pressure won't be the same. Or if we're in a pressure cooker, that external pressure is going to be much higher, and so the boiling point is going to change due to that applied pressure. And so lower external pressure means molecules in the system need less kinetic energy form bubbles. So again, the boiling point happens when we're forming bubbles in the interior of the liquid, okay? And so it looks like this. You know, if you've watched water boil, you will see that we start to form bubbles, you know, down below or inside the interior of the liquid, and those bubbles rise to the surface and then they escape into that vapor phase. So we get this boiling when we have enough thermal energy to cause these bubbles to form in the interior of the liquid, okay? And so when we look at, again, this vapor pressure, you know, when we look at these different vapor pressures, we see that we have different temperatures. So it takes a different temperature to get to a different vapor pressure. So when we think about stuff just happening on its own, that's what we call a spontaneous reaction, where it just happens. And so we know that water boils at 100 degrees Celsius, but can we do a calculation that proves that, you know, 100 degrees Celsius is indeed the temperature at which the vaporization of water is spontaneous? So let's see. Okay, so remember, when we talked about thermodynamics, we mostly focused on enthalpy, right? But I mentioned that there's more to the story, right? The true measure of spontaneity has to do with the Gibbs free energy, all right? And so a phase transition, okay, our phase transition and right now we're dealing with water to gas, or liquid to gas in this situation. Becomes spontaneous when delta G equals 0. And again, delta G is the Gibbs free energy. So we have this thermodynamic equation that looks like this. Delta G is equal to delta H minus T delta S. So for it to be spontaneous, that delta G has to equal 0. If we know delta H and we know delta S, we can figure out the temperature. And we do know these terms. So our delta H of vaporization for water is 40.67 kilojoules per mole, okay? And our delta S of vaporization is 109 joules per mole. All right. Remember, delta S, that's entropy. That's the measure of disorder, and things like to be disordered. Now, there's a problem here, though. What doesn't match up? The units don't. I've got one in kilojoules and one in joules. Now, strictly speaking, a lot of times when we're dealing with these things, like when we do the Clausis-Clapeyron equation in just a moment, we are going to be needing to take R into consideration. R is a constant, and it is in terms of joules. So we're going to convert our delta H from kilojoules to joules. This is super easy, because remember, a kilojoule is larger than a joule. We have 10 to the third joules per kilojoule, so all I have to do is do 40.67 times 10 to the third joules per mole. Boom, done. It's easy. All right, so now I can plug all this in. So for spontaneity, delta G has to equal 0. So 0 is going to equal 40.67 joules per mole minus some temperature times 109 joules per mole. All right? 40.67 times 10 to the third. Okay? All right, and so when we solve for T, T is going to equal 373 K, which is 100 degrees Celsius. Okay? So voila, the temperature at which the vaporization of water becomes spontaneous is indeed 100 degrees Celsius, which is what we see in practice, at least at atmospheric pressure. Okay, so let's talk about that Clausis-Clapeyron equation. So we get this natural log of the pressure is equal to the negative delta H of vaporization over R times 1 over temperature plus a constant. All right, well, that's great if we just want to calculate a value. But what if I want to know, like, hey, I know something at one condition, what's it going to be at the other condition? We need to have a 1 and a 2, and that's where this comes in. So if we take the natural log of the second pressure over the first pressure, and we set that equal to that negative delta H of vaporization over R, we can multiply that by 1 over the second temperature minus 1 over the first temperature. And this lets us make those comparisons. All right, so we're going to do a couple of them. All right, to start off with, we're going to look at dry ice. So the normal sublimation of dry ice happens at negative 78 degrees Celsius. Now I know I just said delta H of vaporization all over the place, but if we are subliming, we're going straight from a solid to a gas, so we're forming a vapor. So this works even with the delta H of sublimation, not just the delta H of vaporization. All right, so we've got this delta H of sublimation. Now, what if we drop the temperature? What if we go down to 100 degrees Celsius? What's our vapor pressure going to be? Now, would we expect this vapor pressure to be greater than or less than 1 atmosphere? Well, we should expect it to be less than 1 atmosphere because if the sublimation happens at negative 78 degrees Celsius, negative 100 is below that, which means we should have fewer molecules that have enough energy to enter that vapor phase, right? Because we're below that sublimation temperature. And so we would expect the vapor pressure to be lower because we don't have as many molecules in the vapor phase. So let's see if this is indeed what we see. Okay, so what I like to do, especially when I'm doing condition 1 equals condition 2 problems, is I like to define all of my variables. That helps me keep everything straight, and it helps me make sure that I have everything in the correct units and take care of any converting before I dump it all into the equation. All right, so remember, we've got the natural log of pressure 2 over pressure 1 is equal to that negative delta H over R. We have a temperature 1 and a temperature 2. So let's see what variables we have. Okay, so we do have a delta H of sublimation. Okay. My software is having issues today because this is not the first problem I have had. I'm going to do this problem. It is not letting me back up to the previous slide. I don't know what is going on, but I've had this crash out on me tonight too. It is being especially touchy. Even normally where I write, it's starting to spaz on me tonight. So I don't know if it's a problem with my iPad screen or what's going on. So I am going to solve this problem. And then I'm gonna pull up a blank slide and I will put up a supplemental video that solves the dry ice problem. Because I'm not gonna record this whole video all over again because this is not the first time I've recorded this video today. So let's do this problem, and then I promise all of you that want to see how that problem is solved, I will solve it. I'm just gonna have to do it in another video because I don't have the patience to record this one again. Okay, so let's try this problem instead. All right, so here's where the boiling point changes if we're at altitude. So this problem lets us look at that. We're looking at altitude of the Pikes Peak, and at that altitude we have a lower atmospheric pressure, 447 torr. So let's figure out what the boiling point of water is at this new altitude. Again, let's define our variables, and this time let's hope that it doesn't spaz on me and advance 2 slides. Cool. Okay, so we have a delta H, yay, a vaporization for water, which was that 40.67 kilojoules per mole. All right, we're using R that has energy in it, so that's our 8.314 joules per mole Kelvin. All right, now, our formula has pressure 2 over pressure 1, all right? It's arbitrary which one you set which. As long as you keep the 1 and 2 straight, it doesn't matter which one's 1 and which one's 2. So pressure 1 would be atmospheric pressure, which is 1 atmosphere. So I'm just going to leave pressure 1 because that's the one on the denominator. Makes the math easy as 1 atmosphere. Okay. So that makes our temperature one 100 degrees Celsius, because that's the temperature at which water boils at atmospheric pressure, which is our 373.15 Kelvin. Okay, so then our pressure 2 is our 447 torr, and our temperature 2 is what we're trying to figure out. What temperature does water boil at this pressure? Now, if I'm using atmospheres and torr, I got to convert one or the other. I converted torr to atmospheres, so I can keep that nice number 1, and we get 0.6276 atmospheres. And then remember, we need this in joules because I've got joules in my R. So I'm going to do 40.67 times 10 to the third joules per mole. Okay, now we're ready to plug this in and solve. Okay, so we're going to get the natural log of 0.6276 over 1 equals negative 40.67 times 10 to the third joules per mole over 8.314 joules per mole Kelvin, 1 over T2 minus 1 over 373.15 Kelvin. Okay, now it's just a matter of scrunching things together, combining like terms, and doing some algebra. All right, so we get negative 4.659 times 10 to the negative first equals negative 4.898 times 10 to the third, which I was in the middle of writing this, the very end, when this errored out on me the first time, which I'm actually now suspecting that it might be the screen on my iPad. Okay, 1 over T2 minus 2.679 times 10 to the negative third. All right, we can continue scrunching things together. I'm going to get 9.512 times 10 to the negative fifth is equal to 1 over T2 minus 2.679 times 10 to the negative third. Continue to combining like terms, we get 2.774 times 10 to the negative third equals 1 over T2. All right, so if you forgot your algebra, what do we do from here? Well, if I have 1 over T2, I raise both sides to the negative 1. All right, so we're going to take this and raise it to the negative first, take this and raise it to the negative first, and that's how we're going to get rid of T2. Get rid of the 1 over T2, so T2 is going to equal 360 Kelvin, which is 86.9 degrees Celsius. All right, does this make sense? We're at a lower atmospheric pressure, so we have less external pressure to overcome in order to reach that boiling point. So that makes sense that the temperature is lower because we have a lower pressure to overcome. All right, I apologize for the iPad glitch. So we're done with this, but there will be a very brief video right after this one where I'm going to go through solving that dry ice sublimation problem for you. Cool. All right.